Okay, describe the set of positive integers for which there is an m. M is even. 2m minus n plus 1 is odd. And
one of them's odd, one of them's even. You don't know which one.
Yes. However, we do have this factor of 2 over here.
Oh, yeah.
Right? Wait, one sec. It's 2n, my bad. It should be 2n. Right, so basically we do have that these two are always opposite sign. Pretty sure k can't be a power of 2 to the k. What if m is equal to 4, let's say?
Yeah, I don't think it would work because then you're multiplying it by an odd number. And that doesn't fit in the powers.
Obviously. Yes. Right, so that's what the greater than 2 condition is. Yeah. Okay, so we know for sure that basically k can't be a power of 2. So k is not equal to 2 to the L. But does it work for any other? Does it work for every other k? So let's say we have arbitrary k, and we can write k as like it's a product of its primes, right? So we have p1 through to pl, let's say. Huh? Wait, who's writing this? Can you speak? Okay, never mind then. There is an m by m grid containing k non-congruent triangles. So for sure, we know that it's not a power of 2 to a power of 2, because this has to be odd, which means it contains, and furthermore, not only does it have to be odd, but oh, it can be 1 actually. In the case where
K can't be 1 because m and n is greater or equal to 2.
yeah, so you have 4 minus 2 plus 1. Never mind. Yeah, okay. So it can't be any power of 2. So we write k as it's.
I think k is greater than 3, right? Greater equal to 3.
Yeah, okay. So k is greater than or equal to 3. From the fact that n and m are, so this will actually, not only that, k is greater than or equal to, yeah, 3. Because the factor of 2 cancels. Okay, so basically you have to consider the odd or any other prime factor of k besides 2. Maybe we consider a small k. Maybe so we want to find the set of all possible things. So yeah, let's have a look at a small one. Let's look at let's say k is equal to 3, yeah? Actually, with the k equals 3 cases, it works. So let's look at k equals 5. So we've got m times 2n minus m plus 1 equals 10. So we can either have m is 1, m is 2, or m is 5. But not m is 5. M is 1 or m is 2. And this thing is 10 or 5. So this would lead us to the conclusion that n is equal to 5. Oh, but we don't want the 1. We don't want the 1. So we only look at this one. This will give us that n is equal to 3. So 2 by 3 works. But what was important here? The fact that whatever k is, but since we have 2k here, we always have the factor of 2 here. So if we can find a way such that 2n minus m plus 1 is equal to k, it always works, right? And we also set m is equal to 2. So we have 2n minus 2 plus 1 equals k. So in other words, n is equal to k plus 1 on 2. All right, so I might have skipped a couple steps of logic here, but basically what I want to show is that for any k which is not a power of 2, I can, for any k which is not a power of 2, I can find a pair mn that does satisfy this equation. Okay, so when k is completely odd, I can just let m equal 2 and then do this. So when k has no power of 2 in it, it's completely like this. Completely like this with no pi. Pi is not equal to 2. Then I just said this thing is equal to k, right? By looking at this equation here. And I set m to 2, so I can divide 2 out. And then I'm left with this. And I can indeed find another pair n. So I have a pair mn of integers which satisfy the equation, right? And this is when k is completely odd. So k has no factors of 2. Now I consider where k is equal to, this is when k odd. Now I consider k even. So I have maybe k is equal to 2 to the j, and then the rest, right? What can I do here? We just set, I think we just set m equals 2 to the j plus 1, right? So then you're going to have 2 to the j plus 1 times 2n minus 2 to the j plus 1 plus 1 is equal to 2 to the 2 times k. So I can cancel one of these. And then when I cancel these, let me undo this. So I have 2 to the j, this whole thing, 2n minus 2 to the j plus 1, or minus 1 because I'm going to add them to both sides afterwards, is equal to k, but k is 2 to the j, p1, pl. Once again, pi is not equal to 2. So I can cancel through the j's on both sides, and I have 2n is equal to p1, pl, plus 2 to the j plus 1 minus 1 all over 2. So since this is odd, taking mod 2, we just have this is 0, mod 2. So it's like odd plus odd is even, right? The same as saying taking this mod 2, this is 0. So in other words, I can divide by 2, and this does end up as an integer. So this is an n. This whole just to be a little bit more precise, so I can have that as 2 to the j plus p1 through pl minus 1 over 2. And that is below. Minus 1 over 2. And note that since j is greater than or equal to 1, this and p1, at least one of these is greater than, sorry, not at least one. Every one of these is greater than or equal to 3, right? So this thing here was greater than or equal to 3 minus 1 over 2. So this whole thing is greater than or equal to 3. Which just means that it satisfies being n is greater than or equal to 2. Does this satisfy everything?
Did you ask me for something?
No. I'm just double checking that this satisfies and that this works. but maybe it would be useful to have a poll to see if people followed what I said. Excellent. Seems like most people are following pretty well. Oh no, the spams have started. But yeah, so to wrap it up, we basically have that the set of all possible things is just k and n excluding powers of 2. That is our conclusion. So that about wraps up this question. If no one has any questions. Yeah, so Michael, you said you had something to say?
Yeah, hold on. So I'll start sharing in a sec.
Okay, let me stop then.